Imagine, just for a second, that you want to order lunch. You pull out your phone, you tap a button, and you just tell your AI assistant, order me the cheapest item from Taco Bell.
Which sound like the ultimate luxury, right?
Right. In theory, it's amazing.
Yeah.
But if you've actually tried to use current web agents to execute a prompt like this, you know the reality.
Oh, yeah, it is not smooth.
It's clunky. It's frustratingly slow. You're sitting there watching the AI slowly click, pause, scroll, pause, completely lose its place. And maybe, eventually, like 10 minutes later, put a bean burrito in your cart.
Hmm.
It is a total latency nightmare.
Absolutely a nightmare.
But today, we're doing a custom-tailored deep dive just for you on a brand new, state-of-the-art generative AI paper that actually fixes this.
And it's a huge step forward.
It really is. It's called JIT Compilation, which stands for Just-in-Time Compilation. And our mission today is to unpack exactly how this transforms your AI from a confused digital tourist into a lightning-fast compiler.
I love that analogy.
Okay, let's unpack this. Before we can really appreciate how this JIT compiler works, we have to isolate the fundamental flaw in current computer use agents, things of browser use or OpenAI's computer use model.
Yeah.
Why are they so painfully slow?
Well, the bottleneck is entirely architectural. I mean, current agents rely on this sequential loop that's known as fetch, screenshot, execute.
Fetch, screenshot, execute. Got it.
Yeah, so when you ask an agent to do something, it looks at the current state of the web browser, usually by taking massive screenshot or grabbing the entire page code.
Right.
And it sends all of that context to a large language model. The LLM processes that enormous context window, churns through its parameters, and then decides on just one single primitive microscopic action.
Like just moving the mouse a little bit.
Exactly. It outputs something like, click at coordinate XY, the browser executes that one single click. Then the agent has to take another screenshot, send it back to the LLM, and wait for it to generate the very next microscopic step.
It's like hiring a world-renowned neurosurgeon and $5,000 an hour to screw in a light bulb, but forcing them to step down the ladder, reevaluate the entire room, and then hiring them again just to flip the switch.
That is honestly the perfect way to capture the sheer waste of compute happening here.
You are using the most computationally expensive resource imaginable for basic mechanical movements.
You really are, and constantly reevaluating the room doesn't just burn through processing power. It introduces this compounding probability of failure.
How so?
Well, every single time the agent calls the LLM for a primitive action, there is a chance the model hallucinates or just misinterprets the screen.
Right, because it's generating an answer from scratch every time.
Exactly. So if a task requires 40 steps, and each step relies on a fresh, on-the-fly inference call, the odds of making it through that entire sequence without a critical error are incredibly low.
That makes total sense.
Yeah, the data in our sources actually confirms this. They found that 45 to 50% of all errors in web automation occur simply because of an incorrect sequence of actions.
Which means the AI is essentially losing its train of thought.
Pretty much, yeah.
It might try to type a search query into a field before it has actually clicked the field to activate the cursor.
Exactly, or it tries to click a hidden drop-down menu item without ever actually opening the drop-down.
So it violates the basic logical flow of the website because it lacks object permanence?
Yes, it just forgets the prerequisites of its environment. So the researchers behind Agent JIT Compilation realized they needed to stop relying on the LLM to invent the wheel at every single microstep.
Which brings us to the first major solution.
Right. This leads to the first major mechanism in the paper, which they call the Invariant Enforcing Tool Protocol.
The Invariant Enforcing Tool Protocol. So giving it a set of rules it cannot break.
Exactly.
But how do you enforce strict rules on a model that is fundamentally designed to be generative and unpredictable?
Well, you wrap its capabilities in strict digital contracts.
Digital contract.
Yeah, instead of giving the agent open-ended access to primitive actions like click here or type this, the researchers engineered a system that provides the agent with cached reusable tools.
Okay.
Think of a tool as a pre-packaged block of code built for a highly specific action. So something like list menu items or add to cart.
Gotcha. So it's not clicking pixels, it's executing a specific function.
Right. But the brilliance of this protocol is that these tools are bundled with rigid preconditions and postconditions that dictate exactly when they can be used.
Let's apply that to the restaurant scenario for a second. The paper tests this on a DoorDash-inspired environment called Dash Dish, right?
Yep, Dash Dish.
So if the AI wants to use the Add to Cart tool, what do these conditions actually look like in the underlying code?
So a precondition is basically a gatekeeper. For the Add to Cart tool, The precondition mathematically checks the current state and dictates that the page must already be classified as a store page.
Oh, so it can't be on the home page.
Exactly. If the AI hallucinates and tries to schedule the add to cart tool while it's still looking at the Dash Dish homepage, the system literally blocks the execution.
Wow, it just stops it.
It stops it cold. It forces the AI to recognize, hey, I cannot order food until I have successfully navigated to a restaurant.
That's incredibly smart.
It is. And then once the precondition is met and the tool actually executes, the postcondition kicks in.
Guaranteeing the outcome.
Precisely. The postcondition verifies that after the item was added to the cart, the browser is still on the store page.
So it mathematically ensures the tool didn't accidentally click a rogue ad that redirected the browser to a totally different domain.
Exactly. And by enforcing these state flow rules at the compilation stage, before the browser even moves, tool ordering violations drop massively.
Do we have the numbers on that?
We do.
Mm-hmm.
The researchers noted that without the protocol, ordering issues caused 59% of task failures.
59%.
Yeah, but with these strict contracts in place, that failure rate drops to just 25%.
Wait, I have a question about this, though. If the tools are these hard-coded contracts expecting very specific page states, doesn't that make the system incredibly brittle?
That is the exact vulnerability you'd expect, actually.
Because the web is so dynamic. We have A/B testing, UI redesigns, random seasonal banners popping up out of nowhere. If a tool expects an add to cart button to be at a specific node and the website updates overnight, wouldn't a rigid post condition just cause the whole automated system to crash?
Yeah, it absolutely would, which is why the protocol utilizes runtime DOM predicates to prevent those catastrophic crashes.
Runtime DOM predicate, so it's actively interrogating the live architecture of the site in real time.
Yes. The tools have what are called pre-check and post-check functions written directly in JavaScript.
Okay.
So a millisecond before the add to cart tool executes, it runs this runtime DOM predicate, which is just a lightning-fast script that checks the live underlying structure of the web page to verify its assumptions.
So it's asking, is the add to cart container actually present in the DOM right now?
Exactly. And if the web page underwent a massive redesign overnight and that check fails, the system doesn't panic and break.
It catches the discrepancy before the physical click even happens.
Exactly. The tool is simply marked as invalid for that specific execution.
Well, that's clean. So what does it do next?
The system then safely falls back to a replanning phase. Or, in worst-case scenarios, it just seamlessly reverts to the slower, traditional LLM agent browsing to carefully read the new layout and figure out what changed.
So it's a built-in safety net that prevents blind execution.
Exactly.
Okay, so the AI has this safe, rule-bound protocol preventing it from making sequential errors.
Right.
But for any complex prompt, say, find the cheapest item, there are dozens of valid ways to write the code to achieve that.
Sure.
It could look at every item sequentially, it could sort the page by price, or it could scrape the entire DOM array. How does the system automatically figure out which valid plan is actually the most computationally efficient?
Well, that heavy lifting is done by the JIT planner.
Here's where it gets really interesting.
Yeah, because when you feed the system a natural language request, the planner doesn't just guess the best approach. It generates multiple different code plans in parallel.
Oh, wow. In parallel.
Yes. It translates your English prompt into several variations of executable code, mixing those cache tools we just discussed, raw Python logic, and any necessary LLM calls.
This is where that shift from a simple chatbot to a true compiler becomes really tangible. The AI isn't just writing code, it is actively auditing its own code's execution cost before it actually runs anything.
Exactly.
How does it mathematically grade one plan against another?
It constructs a control flow graph, or CFG, for every single plan.
A control flow graph.
Think of a CFG as a massive branching decision tree that maps out every possible future state of the program. Node A leads to node B or C, and so on.
Got it.
As the planner traces through this graph, it estimates the computational weight and latency of each path. And the most critical feature of this cost model is how it treats LLM inference.
I imagine it hates LLM inference.
Oh, it heavily penalizes it. The JIT planner applies a severe penalty, specifically a penalty factor of 10, to any plan that attempts to put an expensive LLM call inside of a loop.
Because putting our $5,000 an hour neurosurgeon inside a repetitive loop is a recipe for bankruptcy, both in time and compute.
Precisely.
So if I ask the AI to, say, tell me how many restaurants in my area have fewer than 20 reviews, a naive AI might navigate to the restaurant list, call the LLM to visually look at restaurant 1 and count the reviews,
Yep.
then loop, call the LLM for restaurant 2. Loop, call the LLM for restaurant 3.
And if there are 50 restaurants on that page, that is 50 separate massive context window inference calls.
Which is brutal.
It is. So the JIT planner evaluates that specific control flow graph, sees the LLM node buried inside a loop iteration, multiplies its cost by 10, and just rejects the plan as egregiously inefficient.
So what does the winning plan look like in that scenario?
The planner will instead favor a code path that uses a single tool to scrape all the review data from the DOM into a simple Python array in one sweep. Oh, nice.
Yeah, and then it uses a basic lightning-fast Python if statement to iterate through that array and count the ones under 20.
So it requires 0 LLM calls during the loop itself.
Exactly. It offloads the cognitive work to basic deterministic programming.
It isolates the thinking from the doing.
Yes.
What is the actual real-world time difference between the system picking that naive plan versus the optimal penalized plan?
The researchers actually quantified this exact metric, and the latency gap is massive.
Wait on me.
On average, across their testing benchmarks, there is a 5.3 times difference in execution time between the worst cost valid plan and the best cost plan.
5.3 times faster.
Yeah, so a task that would take 61.7 seconds to execute using the poorly optimized LLM loop takes just 11.7 seconds when the JIT planner forces the optimal Python logic.
That is wild. Taking a minute-long wait down to 10 seconds fundamentally changes how a user interacts with the AI. You stop treating it as this background process and start treating it as a real-time assistant. And the benefits compound, too. When you combine the invariant protocol, keeping the agent on track, with the JIT planner picking the optimal code path, the system achieves a 10.4 times speedup over the standard browser use baseline.
10.4 times. Wow.
Furthermore, because it's executing deterministic Python code rather than relying on hallucination-prone step-by-step LLM logic, it also gains a 28% boost in raw accuracy.
Okay, so the JIT planner has handed us the absolute best, most rigorously audited map.
Right.
But a flawless map doesn't drive the car. The code still has to be physically executed by processors.
Yes, it does.
Managing how that compute power is delegated seems like it could easily become a new bottleneck if not handled correctly.
That is a crucial insight, and it introduces the third architectural pillar of this paper, which is the JIT scheduler.
The JIT scheduler?
Yeah, the scheduler's entire job is to dynamically allocate workers, which are essentially virtual CPUs, to execute the nodes of that optimized control flow graph. It evaluates the task and decides how to deploy resources to get the fastest result.
So what kind of strategies does the scheduler actually choose between? Does it just throw maximum compute at everything?
Not at all, because coordinating multiple processors carries its own overhead.
Oh, true.
To find the perfect balance, the JIT scheduler uses Monte Carlo cost estimation.
So it's running simulations.
Exactly. It essentially plays out the web browsing futures thousands of times in a mathematical sandbox, using historical latency distributions to probabilistically predict how long web elements will actually take to load.
Fascinating.
And based on those simulations, it selects one of 3 distinct execution strategies: serial, parallel, or hedge.
Okay, let's break those down. Serial execution implies a linear approach, right? One worker doing one thing at a time. What scenario makes that the optimal choice?
Well, serial is selected for tasks with low variance and strict linearity. The paper provides a great example. Say the prompt is, how much is a matcha croissant and a regular iced matcha latte at Stone Mill Matcha? To complete this, the agent must navigate to the Stone Mill Matcha page, read the croissant price, and read the latte price. The Monte Carlo simulation calculates that spinning up multiple processors to do this would actually take longer because of the latency involved in initializing the workers and then merging their findings.
So a single focus worker is statistically the fastest path there.
Precisely.
Which leads us to the parallel strategy, which I imagine is the divide and conquer approach.
Exactly. Parallel execution is triggered when a task can be broken down into completely independent subtasks that don't rely on each other's state.
Give me an example of that.
So in the Amazon e-commerce benchmark used by the researchers, a prompt might be, visit the gift, toy, gaming, and cosmetic categories, and for each, report the color of the first product.
Oh, I see. So rather than one worker clicking gift, waiting for it to load, reading the color, then clicking toy, the scheduler just deploys 4 separate workers simultaneously.
Yes.
Worker 1 takes gift, worker 2 takes toy, and they all hit the endpoints at the exact same time.
Exactly. The math proves that running those independent actions concurrently saves vastly more time than the microsecond cost of spinning up the extra workers.
Makes total sense.
But the third strategy, hedging, addresses the most chaotic aspect of web browsing.
Hedging. Let's look at the specific task for hedging from the source material.
Hmm.
It's place an order for any type of sub-sandwich, keep the total under $30.
Right.
According to the paper, navigating complex restaurant menus to find an active Add to Cart button is highly variable. Sometimes the DOM is clean and the agent finds it in a second, but sometimes the menu is buried under complex UI elements and it takes the agent 40 seconds to isolate the button.
Yeah, that variability is known as a heavy tail distribution. Most of the time it's fast, but that minority of the time when it's slow, it is punishingly slow.
Right.
So to combat this, the scheduler deploys the hedge strategy. It races multiple redundant workers against each other.
Wait, it raises them.
Yeah. It gives 4 distinct workers the exact same sandwich order, sends them into the menu structure simultaneously, and simply accepts the result of whichever worker finishes the checkout process first, immediately terminating the others.
So hedging is basically sending 4 interns out of the office to buy the exact same sandwich from the exact same deli, and the moment the fastest intern walks back through the door, you just fire the other 3.
I mean, that is a brutal way to phrase it, but yes, computationally, that's what's happening.
It's an incredibly fun concept, but isn't that wildly wasteful of compute? You are essentially burning electricity on redundant tasks.
It is entirely wasteful if your primary metric is server cost or electricity. But the JIT scheduler isn't optimizing for raw compute budget, it is mathematically optimizing for absolute minimum time latency.
Oh, okay.
In a heavy tail distribution where an element might inexplicably take a minute to load for one worker, deploying 4 workers makes it statistically highly probable that at least one of them will catch the fast path and finish in 3 seconds.
You are intentionally spending compute to guarantee a seamless, instantaneous user experience.
That's the perfect way to phrase it. And by dynamically toggling between serial, parallel, and hedge strategies based on those probabilistic simulations, the JIT scheduler squeezes out another massive efficiency gain.
Oh, more speed.
Oh yeah, it achieves a 2.4 times speed up and a 9% accuracy improvement over OpenAI's fine-tuned computer use model purely through better resource delegation.
This is unbelievable. So we have 10 times speed ups from the planner auditing its own loops,
Yep.
2.4 times speed ups from the scheduler running Monte Carlo simulation,
Exactly.
and a strict invariant protocol ensuring the AI never gets lost. Fully autonomous, lightning-fast web surfing. But we have to look at the friction.
There's always a catch.
Right. What is the real-world limitation keeping this specific JIT architecture from being pushed out in a software update tomorrow morning?
Well, the catch is the upfront investment. This system does not naturally understand a new website the second it looks at it. To achieve these compilation speeds, it requires a significant offline setup cost. Before the JIT compiler can perform seamlessly on a specific platform, say a complex airline booking system or a major grocery app, it requires 25 to 90 minutes of offline trace collection per application.
So it has to scout the territory and build the map before it can run the race.
Precisely.
What is it actually doing during those 90 minutes?
An agent is slowly, methodically clicking through the application in an offline environment. It is identifying the DOM schemas, measuring how long pages take to load to build those latency distributions for the Monte Carlo simulations.
All right, for the scheduler.
Yes. And most importantly, it's synthesizing those custom JavaScript tools and writing the rigid preconditions and postconditions we discussed earlier. It is a very heavy initial lift.
And the research highlights another critical vulnerability too, which is stochastic environments.
Yes. Web environments designed to be intentionally unpredictable. The most obvious examples are bot detectors, aggressive rate limiting, or CAP-TCH.
CAPA-TCAs are the worst.
They really are. If the agent is flying through a checkout process and the website suddenly throws up a CAP-TCHA, the strict post condition of the JIT protocol will immediately fail.
Because it's suddenly not on the page you'd expect it to be on.
Exactly. The system will realize the DOM structure is wrong, mark its tool as invalid, and instantly lose its massive speed advantage. It is forced to revert back to the slow, sequential, expensive LLM reasoning just to parse the CAP-TCHA.
Which means, for you listening, this tech is not currently designed for casually browsing a random, obscure blog you visit once a year.
Definitely not.
The 90-minute mapping cost makes that impossible. This architecture is built for enterprise automation or your daily, highly repetitive tasks on massive platforms.
Right.
Think Amazon, Gmail, GitLab, or DoorDash. Platforms where that upfront cost of caching the tools and mapping the latency pays compound dividends every single day, turning 5-minute daily chores into 5-second background processes.
Honestly, to synthesize everything we've uncovered today, we are witnessing a fundamental architectural shift in artificial intelligence.
We really are.
Generative AI is evolving from a conversational entity that simply outputs text into compiled agentic software. By enforcing strict digital contracts, mathematically auditing code before execution, and dynamically scheduling compute power to defeat web latency, models are moving from talking about the internet to actively, flawlessly operating the internet on our behalf.
And that leads us to a final provocative thought to leave you with today. If AI agents become this incredibly fast and dominant, if they're perfectly compiling our natural language intent into raw, parallelized code to navigate the web at lightning speed, will the websites of the future even need graphical user interfaces?
That is a great question.
If a human never actually looks at the DoorDash menu because an AI JIT compiler fetches the data in milliseconds, will we even need buttons, drop-down menus, and aesthetic images? Or will the future web slowly shed its human-readable design, becoming a massive, invisible ocean of pure data endpoints, designed exclusively for AI agents to negotiate and navigate for us in the dark?
It's a profound paradigm shift, really redefining who the internet is actually built for. Thank you for joining us on this deep dive. Keep questioning and keep exploring the edges of what's possible.
Until next time.